Welcome back to the Ductile series of videos. Now in this video we're going to cover just some very basic ways that steel elements are recombined to make different types of structural and constructional elements. Now a broad range of structure types can be developed from basic steel profiles, and I guess it's the flexibility of steel that allows the elements to be reconfigured in this way. Now it's a way, particularly with steel, the balance between the added labour and the cost of the material to enhance its properties is a fairly even cost-benefit analysis. Because steel is very expensive, it is seen as a sort of a more precious material, and so to try and stretch it and to get more out of it, even though that comes at an added expense of extra labour and material handling, most of the times it's worth it. Now the simple universal beam again is the workhorse of most of steel fabrication. Now there are certain things that we can do with the universal beam, and the first is we can actually preload it by pre-cambering it or bending it upwards. Now the logic of this is that steel as a plastic, as a very sort of stiff material and a very predictable material, means that we can figure out the dead loads of a building and bend the steel elements upwards a little bit, and then fix the rest of the construction on top of that, with the view that once the load comes onto it, the beam will then flatten out. Now in practice this is it does set up a complexity during construction, because obviously we're not working with flat and horizontal elements, so in a lot of architectural construction it's not used quite so much, though it is used in quite large span structures, and also in other applications such as steel work used in infrastructure, and even things for like truck beds and so on, which are often pre-cambered so that they can be thinner and lighter to take more load. Another way that we can treat a standard universal beam is to cut it through the center and then to re-weld it together. The common term for this is a castellated beam, and by cutting a series of zigzag hexagons shapes through the middle of the beam, we can split a beam in half and then offset it and then re-weld it back together to give us additional depth to the beam, which also has the added benefit of creating a series of service holes through the middle part of the beam where there's very little load transferring through that. As we saw in an earlier beam or truss elements at the Hawken building, the other thing that steel is very good for is just using off-the-shelf components to make lightweight web-type structures or trusses. Now there's quite a lot of examples of flat trusses that are very efficient with the use of steel, and often the use of equal angles paired up is a very simple and effective way of creating these elements. Now here we can see a Pratt truss where the diagonals are more or less pointing down and oppositely configured from the center outwards, which is contrast to the Howe truss where the diagonals are going in the other direction. And this is again counterpoint with the Warren truss, which is I guess the more common of the truss beams, where for lightweight trusses in particular, where the elements through the middle, the diagonals are basically zigzagging all the way through. Well, that's just a basic introduction to the concept, I guess, of how steel can be reconfigured, or standard steel elements can be refigured into more efficient structural elements, so that again we can make the absolute most out of the steel, and minimize the amount that we have to use, and minimize, I guess, as a consequence, our carbon footprints, by using such a high energy material. Stick around, there's still a few more videos to come, and hopefully you find this informative.